pretty common in a lot of engineering and other physical, real-world situations to have only limited information about some function that you're trying to understand. So for example, suppose that we have an object moving back and forth along a line. It has a position function, but you aren't in general going to actually know what that position function is. You might know bits of information about it, but you won't know a full-blown formula for it usually. So suppose that we do have some limited information about this function. Suppose we know that s of 4 is 5 and s prime of 4 is negative 2. One thing that we might hope to do is, because we know about this position function at time 4, we might hope to at least estimate this position function for t values that are close to 4. Of course, since we don't really know what's happening far away from time 4, there's little hope of knowing what the position function is for t values far away from 4. But it seems like close to 4, maybe this is enough information to have a decent estimate. Well, let's draw a picture of what this information is telling us about this function, this position function s. So here's our s-axis and here's a t-axis. So at t equals 4, we know we're at position 5. So here, and since s prime of 4 is minus 2, that means that at this point, the slope of the tangent line to the function looks like this. Now we don't know what the function actually looks like for other t values. So, maybe it curves like this, or maybe it comes from here and then goes that way. I mean, we have no idea really. But you can see that as long as we stick to t values near 4, the graph has to follow this general trend that would produce a tangent line whose slope has minus 2. So what we can do is, for t values near 4, we can just estimate that this function is approximately the tangent line at 4. So, well, what is the tangent line at 4? Let's come up with an equation for the tangent line at 4. Let's do it over here. So we know the slope of the tangent line at 4. That's just the derivative of the function at 4. And that one is one of the things we know. Also, we know a point on the tangent line because we know that s of 4 is 5. And that means that the point 4, 5 is on this tangent line. So that means that the equation for the tangent line is going to be y minus 5 equals minus 2 times x minus 4. And if we move all of this to the other side, we get y equals, let's see, minus 2x and then plus 8 minus 5, so that's plus 3. Sorry, plus 8 plus 5, so 13. Yeah. Okay. Well, this is the... Oh, I've used x and y. Really, I should have been using t and s, I guess. So this should be a t, and this should be an s, this should be an s, this should be a t. But you can see that what we have here is the equation that we want right here. So s of t is approximately minus 2t plus 13. But I think this is one case where actually multiplying everything out makes it less clear what's going on with this formula. So let's leave it in the original form. So we had minus 2 times t minus 4 plus 5. And this minus 2, this is here because that's the derivative at 4. Here's our 4. And this 5 here, this is s of 4. Right? And you can see that the way that we came up with this tangent line, or the formula for this tangent line, it didn't actually depend on what any of these numbers were. The only thing that mattered is the role that they all play in the general setup here. So if we wanted to do this in general, we could, for any function, I guess what we need to do is first pick an x value a fixed x value where we're going to approximate the function. This is called the base point. And to make this whole thing work, we have to know f of a and f prime of a. And then for x near a, we can approximate the unknown function with its tangent line, which is, right, we need the derivative at our base point, so that's f prime of a times x minus the base point, so x minus a, plus, and then here's the value of the function at the base point, so f of a. So just from knowing the value of the function at the base point and the value of the derivative at the base point, we can make this approximation near the base point by replacing the function, which we don't know, with the tangent line, which we can work out given these two bits of information. This way of approximating a function is called linear approximation, because we're approximating some unknown function with its tangent line. So we're replacing it with a line, so we're calling it linear approximation. So in general, right, if you know a base point, you know the x value, then for x values near the base point, you can approximate the function with f of a plus f prime of a times x minus a. Let's look at a couple examples of this. So first of all, let's suppose that f of minus 3 is 4, f prime of minus 3 is minus a half. Let's use linear approximation to approximate these two values of the function. Now, we can't find these values exactly because we just don't know enough about the function. But these x values are close to minus 3. Right? So we can, for each of them, we can use linear approximation. So let's work out linear approximation. What should our base point be? Well, we don't really have any choice for our base point. The base point has to be an x value where you know the value of the function and its derivative, and the only x value where we know the function and its derivative is minus 3. So minus 3 is going to be our base point. So for x values near minus 3, this function is approximately f of minus 3 plus f prime of minus 3 times x minus the base point, minus 3. So f of minus 3, that's 4, plus minus a half times x minus minus 3, so x plus 3. All right, so now we can evaluate this linear approximation at these x values to approximate the function. So f of minus 2.8 is approximately, now we can just plug 2.8 into our tangent line. So 4 minus 1 half times minus 2.8 plus 3. So 4 minus 1 half times 0.2. So 4 minus 0.1, that's 3.9. Okay, we can do the same thing for any other x value near minus 3, for example, negative 3.1. So f of minus 3.1 is approximately 4 minus 1 half times negative 3.1. Right, this is the x value where we're making the approximation, minus our base point, so plus 3. So 4 minus 1 half times, looks like minus 0.1. So this is 4.05. Okay. You can see if you have a linear approximation based at a certain x value, you can use that multiple times for any input that's close to that base point. What I mean by close, I'm going to leave vague. It actually depends on sort of how much this function wiggles around, which we don't know at the moment. All right, let's look at one other example, something that's a little more applied, I guess you could say. Suppose that we live in the age before computers or calculators, and suppose we want to find a good approximation for the square root of 9.01 without doing a ton of work. Well, we're talking about the square root function here, so let's name that function. So let's call it f of x. And before calculators and computers, this function was actually hard to evaluate for a lot of inputs. But there are some inputs where the square root function is easy to evaluate. For example, at 9, f of 9, that's the square root of 9, that's 3, right? So there's an input very close to 9.01 where we know the value of the function exactly. Also, the derivative of this function we can work out. It's 1 over 2 root x. We can evaluate that exactly at 9. So we get 1 over 2 times square root of 9 is 3, so that's 1 over 6. So this is enough information to write down the linear approximation near 3. So, near 9. So for x values near 9, our function, which remember is the square root function, is approximately f of the base point, so f of 9, plus f prime at the base point, f prime of 9, times x minus 9. So f of 9, we said that's 3, plus, and then this derivative was 1 over 6 times x minus 9. All right, well now we can plug in the x value we really wanted to know about. So the square root of 9.01, that is f of 9.01, we can plug this into our linear approximation. So it's 3 plus 1 over 6 times 9.01 minus 9. And I need approximate here, not equals. So this is 3 plus 1 over 6 times 0.01. And 0.01 is 1 over 100, so this is 3 plus 1 over 6 times 1 over 100. So 3 plus 1 over 600. So 3 and 1/600th. That's approximately the square root of 9.01. So how good does this approximation do? Well, we do have calculators. So just to see how good this sort of quick and dirty approximation does, let's compare the value of 3 and 1/600th according to the calculator. So this is 3.0016, and then this 6 repeats forever. And if we take the square root of 9.01, we get 3.00166620, and then some more decimals after that. So you can see this quick approximation that just took a moment to calculate, it actually gets this square root correct. Well, it's no surprise that it gets the 3 right, but beyond the 3, it looks like it's correct out to one more place than I wrote down. Right? It's correct all the way out to this place. So that's 6 decimal places, just from a quick linear approximation. You can see how this would be a really valuable technique in the days before automated computing, where every calculation had to be done by hand.